Newton. He was a pretty smart dude. That's why we're still talking about him 300 years later. Now, when people started thinking about forces and what was going on with pushes and pulls in the world, they realized pretty quickly that pushing and pulling on something was going to cause it to move. So the Greeks really believed that the important distinction in kinematics, which is movement, kinematics and movement are the same topic, they thought that the big overarching categories was things that were moving and things that were not moving. So things that were moving, they had a certain set of laws and things going on with forces and patterns. Things that were not moving, so they were at rest, they had other patterns going on with them. So the Greeks kind of thought, all right, if I have an unbalanced force, I'm moving, and as long as my forces are balanced and they all add up to zero, that's when I'm not moving. And you know what? It really doesn't work that way. They really didn't get very far with that line of thinking. It wasn't until Isaac Newton realized that the important distinction was between things that are accelerating and things that are not accelerating. If we have an unbalanced force, that means that we are accelerating, we are speeding up, we are slowing down. And when we have balanced forces, we are either at rest or just moving at a constant velocity. So he wrote 3 laws to try to describe that thought process. So his first law is trying to describe what's going on with balanced forces. Newton's first law states, objects at rest will stay at rest. And objects moving at a constant velocity will stay at a constant velocity unless acted upon by an outside force, or sorry, not outside force. He used the words outside force, but a more accurate term would be an unbalanced force. So that's what we've been studying all unit, balanced forces, things that are at rest or things that are moving at a constant velocity. It's in Newton's second law that he really tries to describe what's going on with unbalanced forces. And he says that an object's acceleration is directly proportional to the unbalanced force and inversely proportional to the mass. Now, we haven't talked about this at all this unit. We've never really touched on things that are speeding up or slowing down, because that's the whole topic of our next unit. All that we are going to do next unit is talk about Newton's second law. So for now, we'll just leave this one behind, and instead we'll turn to Newton's third law. Newton's third law is kind of the black sheep of the 3 laws. The first 2 are very clear. They're setting out his broad categories for how to think about forces in motion. You know, balanced forces means at rest or constant velocity. Unbalanced forces means you're accelerating. Newton's third law is trying to describe why that might be happening, and so he's just talking about forces between objects. And Newton's third law states that all objects Whoops, sorry guys, I wrote the wrong thing for a second. I meant to write all forces come in pairs. The forces in the pair are equal in magnitude and opposite in direction. Okay, you can see why this is kind of the black sheep of the three laws. It's kind of the hardest one to understand what Newton was trying to get at. All forces come in pairs. The forces in the pair are equal in magnitude and opposite in direction. What? Well, think about what you're probably doing right now. Right now, you're probably sitting in a chair. So you know that you are exerting a force downward onto that chair. You are certainly pushing that chair down. But you also feel a force from the chair. That chair is trying to push you back up. That is an example of a Newton's third law pair. Another one, you give your friend a high five, right? You give him like a really good high five. You know that because by swinging your arm, you exerted a force on your friend's hand. But you get a sting as well because your friend hit you as hard as you hit them. If you try to hit them harder, right, like you swing with, a greater velocity, you really put your shoulder into it, yeah, you definitely hit your friend harder. But your friend hit you back just as bad, and you know because your hand really starts to tingle, right? When you give a really good high five, you definitely get a very tingly hand from that large force. Let's try to look at perhaps a force diagram, and that will help us identify the Newton's third law pair. So let's think of some kind of an example. And honestly, the you sitting in the chair example is pretty good. So here is you, and you're sitting down in this chair. Well, I guess we have to draw the chair first. There. We'll change the color. There we go. There's you sitting in a chair. Now, why don't we try to draw the force diagram for you? So I'm going to draw the force diagram for you over here. You have mass, so you know that there is a force of gravity on you by the Earth. And then you're sitting in this chair, so you know that that chair is giving a normal force on you. And those, I think, are the only forces that are acting on you. If we draw the force diagram for the chair, well, the chair also has mass. So there is a force of gravity on the chair by the Earth. And then there's you pushing down on that chair with your butt, right? So there's a normal force on the chair by you. And then that chair is sitting on the floor, so that floor has to push up on the chair. And that floor has to push up the same amount that the force of gravity and the normal force by you are pulling that chair down. Now, if I ask you to identify the Newton's third law pair here, I want to know what forces are on you by the chair and on the chair by you. Because that's what Newton's third law is all about. It's all about how objects interact together. So this is the force of the chair on you, and this is the force of you on the chair. So according to Newton's third law, these need to be equal in magnitude, so we can give them little hash marks, and they're opposite in direction, which we can see by the direction of the arrow. So that is our Newton's third law pair, and this is why I was asking you guys to do this lovely on-by notation on all of your force diagrams. Because by using on-by notation, it's really easy to pick out the Newton's third law pair. You just need to switch the two objects. On you by chair, on chair by you. That's the third law pair. Now, Newton's third law is always true, always, in every scenario. If we go back to what we wrote on the previous page, all forces come in pairs. The forces in the pair are equal in magnitude and opposite in direction. We didn't specify that that's true when we're at rest, or that's only true when we're moving at a constant velocity, or that's only true when we're accelerating. No, it's true always. And especially next unit, we'll talk about how that can still be true even if something is accelerating.